This is the derivative of a composition of functions, right? Composition just means you take one function, in this case g of x, and then slip it inside of another function, f of x, right? So here you have f of g of x. Well, chain rule tells you that you would first take the derivative of the outside, which is f, right? And then we keep the inside function the same, and then multiply by the derivative of the inside function, g of x, just like this right here. But this seems kind of random, so where did this come from? Well, as with anything, we can actually go back to the definition of the derivative, and that's the limit definition. I'm going to use h here instead of delta x, because they kind of represent the exact same thing, just a change in x, right? But we can start writing it down. The first term right here, we just take the function we're trying to take the derivative of, which in this case is this weird thing. And then we plug in an x plus h, or an x plus delta x, same idea. And then we subtract off just that function itself with an x in it. And then we divide everything by h. Okay, so as of right now, this looks kind of weird, right? What can you do with this that's actually going to do anything to help simplify? Well, you can multiply by a 1. But what is 1? A 1 is just anything divided by itself, right? So we're going to choose a very specific anything. That's going to be g of x plus h minus g of x, right? G of x plus h minus g of x. Now you may be wondering, why are we choosing this specifically? Well, you'll see in a second. But yeah, this is just the same thing divided by itself, right? So it's just going to be the same thing as multiplying 1, meaning this guy doesn't remain changed. It's still the same value. Okay, now we're going to do a quick swap. We can kind of combine these fractions, right? If we combine these fractions, then, well, first we have to put this guy in brackets, and we have to put this in brackets too, because these are two things that are multiplying with each other. The second thing is, notice how the denominators are going to multiply. Well, if you remember, a times b is equal to b times a. It doesn't matter what order you multiply it in. So what we can do is just swap the order of multiplication, right? Take this g of x plus h minus g of x guy and plant it in the denominator of this first fraction right here. So g of x plus h minus g of x. And then we multiply by the h that we already have. Like that. So the value still stays the same. So that's the major step to getting this done. Now all that's left is, remember that the limit of a product, you can just take each factor, right? There's one factor here, which is this bulky guy, and then you have this other smaller factor here, right? You can take the limit of each of them first. So we can take the limit of this guy first and the limit of this guy. Like we can do it individually, right? And then just piece it together at the end. So what happens if we take the limit of this thing right here? This, if you recognize it, is just the definition of the derivative of g of x, right? Limit as h approaches 0 of this guy is just g prime of x. It's the derivative of g of x. But what about this factor right here? Well, now we're going to make a quick substitution. So this denominator looks kind of complicated. And I know we multiplied it in. We kind of did it to ourselves. But we're going to try to deal with it. And how are we going to do it? Well, notice here how in the definition of the derivative of g, we just have one variable in the bottom. So what if we just make this one variable? But how do we do that? Well, we can make a substitution. Maybe let's call it k, right? Let k equal to this g of x plus h minus g of x guy. Now notice that h right here is approaching 0. So when h approaches 0, this first term right here goes to g of x. And g of x minus g of x is just 0 too, right? So that means when h approaches 0, which it does, right? That's the limit that we started out with, then k also goes to 0. So as h goes to 0, k goes to 0. So kind of write it like that. Other thing, so we know how to deal with the denominator now. Just call the whole thing k. But how do we deal with this guy right here, right? Because we if we're gonna write one thing in k, might as well just write everything in k, right? But right here, what's remaining inside this first term is this h guy. So how do we get rid of it? Well, pretty simple. Take a look at this substitution that we have going on here. We can just go ahead and isolate the g of x plus h, right? How do we do that? Well, on both sides of this thing, we add g of x. So k plus g of x is equal to what's remaining on the right-hand side, just g of x plus h. Okay, so what we see now, based on the substitution that we're making, is that g of x plus h, which is what's going on in here, is equivalent to k plus g of x. Nice. So we can go ahead and rewrite this limit. So remember that we switched away from using h, right? Now we're using k. Now we're using k. Now we're using k. So what's the limit now, right? We can't just plug it in, right? We can't just replace h with k. Well, we already did the math for that, right? We saw that if we take a look at this expression right here, equation, our original limit had h going to 0. So if we did that, we saw that k would also go to 0. So based on this justification right here, now we can safely say that, well, yeah, k is also going to go to 0. Now let's work on the numerator first. So we have this f of g of x plus h. But remember that we don't want any more h's inside of the expression that we're dealing with. So we went ahead and replaced it with this guy, which came from this equation up here, right? So instead of g of x plus h, right, we can go ahead and write k plus g of x, or g of x plus k. Okay. This last term remains unchanged because, our substitution took us away from h, but there's no h in here. So just leave it be. Now take a look at the denominator. This is the whole reason why we made the substitution. Because that way the denominator would look nicer, right? We want it to just be this single variable, kind of like how it is in the normal definition of a derivative. So now, if we called the whole thing k, so let's just go ahead and replace it with k. So this whole thing, actually, through this substitution, it doesn't change value. It's just equal to this much simpler looking guy right here. And then, of course, we have this g prime of x multiplied on the side. Now, it still might look kind of confusing, right? Why is g of x in there? Well, if we just went ahead and replaced g of x with u, so I'm going to take a note, we're replacing g of x with u, just for the sake of, simplicity, then what do you have? F of u plus k minus f of u all over k. This kind of looks like the definition of a derivative, right? Except for one thing. Instead of an h, we're using k's. And instead of an x, we're using u's. So, what is this guy right here? It's just the derivative of f, right? Except now, the input is going to be a u instead of the x. So, this whole thing right here is literally just f prime of u, okay? And then we're multiplying by g prime of x. Okay, but what is u? Well, earlier, remember that we had g of x's here and here, right? I just replaced it with u to make it simpler to think about, right? U acts the same way as x, right? But if we just go ahead and replace it, right, with what we originally saw it was equal to, well, now we get that this is equal to f prime of, instead of u, we have g of x, right? So we plug in g of x, and then we still have this g prime of x guy sitting out back here. And this right here is exactly equal to what the chain rule is. So that's where chain rule comes from. It's a little bit complicated to find, but it's very important for a lot of stuff in differential calculus, right? There you go.